Thank you. So I want to thank the organizer to giving me a chance to speak here. My name is TE-SHENG Lin. I'm from National Yangming Jiaotong University in Taiwan. And I'm going to speak about a feature capturing PINN for Stokes interface problems. And the PINN stands for physics-informed neural network. So essentially, this talk is about numerical method, how we use neural network to solve partial differential equations, in particular the Stokes interface problem. And this is a joint work with some of my collaborators, Minju Lai in National Yangming Jiaotong University, and Wei Fan and Yu Hao from Central University and University of Kaohsiung. Okay, so I know that the audience here might not be so familiar with how to use neural network to solve PDEs, so I will spend a couple slides to tell you what we are doing for this one, and then how to introduce you what is the neural network and what is the PINNs. Okay, but this is my previous work on syndically thin in a funnel, or this is a relative particle, how this particle and swimming on an isotropic solvent background and see very interesting trajectories. But more or less, anyway, so once you have a problem that you want to study, you write down the equation, you analyze the equation and analyze the problem, you simplify it, and at some point you need to do some simulation. Okay, so for this one, you need to have a partial differential equation on the funnel on a quite a strange geometry, and this one is on two-dimensional domain where you have a circular disk, or you can change it to some different shape. But anyway, you need to use some numerical method to solve the problem. Okay, so recently we are getting interested in how to use neural network and as a new numerical method to solve partial differential equations. But the first two questions we want to ask is, when can neural network be used to solve PDEs? And why can neural network be used to solve PDEs? Okay, so when we can use neural network to solve PDEs is happen when the traditional methods are hard to implement. In this case, we want to use some new method to overcome these difficulties, right? And then to potentially overcome the curse of dimensionality when solve high-dimensional PDEs. As we know that the curse of dimensionality, that if you use some, say, 1D problem, you can use thousands or million points. But in 3D, if you have grid-based method, then in each dimension, then the point is much less. Okay, so that's the curse of dimensionality. And we want to explore some possible hybrid methodologies. So we combine neural network with a traditional method And then why can neural network can be used to solve PDEs? We have universal approximation theory and tell me that the network function is really capable of doing that job. And then we have increased the computational power. And then right now, neural network can be implemented on GPU. And GPU is really optimized to compute or to evaluate this kind of function. And ease of implementation in platforms. Okay, so now the coding is much, much simpler. Okay, so just give you some kind of sense of the difference between traditional method and machine learning method. So my personal background is from finite difference method. So I know quite a lot of finite difference and spectrum method. Finite difference is the difference in approximation for derivative is very, very easy to implement for regular domain, but it has a low order of accuracy in the sense of first order or second order or fourth order, something like that, depending on the grid you choose. And the spectrum method is spectrum accuracy, but not necessary to have fast solvers. Yeah, and for finite element method, of course, it's capable of irregular domain, but again, you need to generate mesh. It has relatively low order of accuracy compared to spectrum method. So you have radial basis method, which is mesh-free, can do irregular domain, but very often the resulting matrix is your condition. Okay, and the machine learning method like the one I want to introduce today is much easier to code and learn the solution directly. It's mesh-free. It's applicable to high-dimensional problems, but often we don't have explainability or interpretability. Yeah. Okay, so a bit of what is neural network. So the neural network, you'll see the neural network always looks like this one. It's a deep neural network. This is a neural network for a single neuron. So if you have a single neuron, you have an input layer, which is really the input variable that you have. For this one is x1 to xd. Then what it's done is to multiply each input neuron by a value called weight. Okay, so this one is W1, W2, and 2WD here. You multiply them together and you sum them together and adding this B. So the output of this single neuron will be W transpose, where W is the vector from this W1 to WD, and then so you are essentially doing the inner product between this vector and that vector and adding a B, and to pass to the sigmoid, or sorry, the activation function sigma here to give you a single output. Okay, so that's how it works in one single neuron. Then you can have a lot of neuron in the first layer, another neuron in the second layer, and you combine everything together. So this is a very typical diagram you see in the deep neural network. So for this one, it's a three-dimensional 3D input. So you have three neurons in the input layer and one neuron in the output layer. Okay. But anyway, when you write down this function directly, so suppose you have just this guy with three neurons, and the function that you have exactly looks like this one, the sigma W1x1, W2x2, W3x3 plus a B. Okay. And you can write down this function, and you know that this is just a composite function, right? You have so many variables and pass through a nonlinear function. And then, so you know how to take the derivative of this guy. It's just calculus. Okay, you take the derivative to x1, so you have sigma prime of everything here inside, and take the derivative to the inside, right, which is W1. Okay, then you can take second derivative. So all the derivative is available. Okay, and the regularity of this function really depends on the. Sorry, I might have screensaver somewhere. Yeah. So the regularity of this guy depends on depend on the activation function. So if the activation function is smooth, then this function is just smooth, because what's inside is just a linear combination. Right? It's infinitely differentiable. Okay. Okay. So about the approximation theorem, then we have some back called 89, which is saying that for any continuous function, then you have a one hidden layer neural network such that the infinity norm between the neural network and the function you want to approximate can be less than epsilon for any epsilon. Okay, but it didn't tell you how wide the network is. But anyway, you have L infinity approximation here, and in Mascas 96, he said that for any function in solar space, there is a one hidden layer neural network for which you have kind of a spectrum approximation in P norm. So this is the number of neurons here, which is n, and it's n to the next r over s power. Okay, and this is about a function value. So you have infinity norm, you have a P norm, and how about derivative in Mishra 21? It shows that there is a neural network for any function. You have a neural network such that the surplus norm can be less than epsilon. So this one has the function and the derivative of this function. Yeah. Okay. So let me go back to this one hidden layer neural network. It looks like exactly just like this one. So it's a one hidden layer. So you have x and pass through some weight and bias and activation function. You sum them together, and so it looks like this one. What's interesting is that Fourier series is in fact a one hidden layer neural network. So if you write down a Fourier series in sine cosine, this is sine kx, cosine kx with some coefficient ck and dk, then this cosine is essentially sine kx plus pi over 2. Right? And you notice that if I have my activation function is exactly this sine, then this ck or dk will be my coefficient here, and what's inside is this weight will be the k, and the bias to be 0 and pi over 2. So you can think of this one hidden layer neural network to be a kind of a generalized or more general kind of Fourier series. Right? So if you choose activation function to be sine, you fix this weight and bias, and for this Fourier series, we know that only the coefficient need to be trained or need to be found. While in the neural network, the difference is we fix the activation function, but all the weight and bias and coefficient need to be found. Okay. So in traditional method, we solve the problem by finding all the coefficients ck and dk, while in network method, we solve the problem by finding all the ck, the coefficients, but also the weight and bias. So it's more parameters to be found. And it's essentially nonlinear. Okay, so this is the physics-informed neural network. So what it says is that there's a problem they want to solve. So we just we represent this solution of this problem by a neural network. As I just showed in the previous page, the neural network is just a function. It's a function. So you have the solution you want to find has a variable x and t. Then your neural network also is a function of variable x and t. It's the same. And what's the difference is just you need to find all the parameter p here. Okay, you need to train this model. And to train this model, what's the requirement to this network? The requirement is that this network needs to satisfy this differential equation, this partial differential equation with some given initial and boundary conditions. So it's a plug-in. So all we need to do is to set up a loss. The loss is just to say that the first PDE equal to 0, so you want to have this guy to be as small as possible. You need to have the boundary condition and initial condition, and some of them to be as small as possible. Okay. So that's a mean square loss. Okay. So that's the essential idea of this physics-informed neural network. You assume that your solution is a network, and you train the model. Right? The train the model by asking your model, your parameter, to minimize this loss, which is the mean square of every single constraint you have. Okay. And to train model, we should have like training point, validation, and test set to make sure that, and really every single point in the domain should try to satisfy this equation or try to minimize this loss. Okay. So one thing is that for this kind of physics-informed neural network, this is like what you are solving using traditional method. For a given problem, you use traditional method to solve it, then you find a solution for this single problem. For physics-informed neural network, it's the same. You solve the problem, you find a network, but this network is very specific for the problem you want to solve. So if you change, let me say again, if you change this G, you need to change the network again, you get different network. So for every single boundary or initial condition, you need to train one network to satisfy this equation. Okay, so that's the Stokes interface problem. So this is two different formulation. This one is the image interface formulation. This is the image boundary formulation. Okay, I think you are very familiar with the equation, so I'll skip here. So this is the problem they want to solve using neural network method. And traditional method, like image interface, we need to have a lot of grid points along the interface, and we need to calculate the corrections along every stencil near the interface. Then there's a correction here. Then we can use the fast Poisson solver or any kind of Poisson solver to solve it. But to find a correction is not that easy, in particular in 3D. Okay, so that's a problem we want to solve. We want to solve this additive interface problem where the U, this solution is a network. So the problem needs to satisfy this guy, that's an elliptic equation with a jump boundary condition. So at each interface, there's a jump, and the normal and the derivative has a jump. And also in the outside, there's a boundary condition here. So this beta is either piecewise constant scalar function or a matrix function, where this bracket denotes the jump discontinuity. And the crucial point is that the solution is discontinuous. Okay, so the solution looks like this guy, and that's the domain. One of the examples of these domains. So the question is, how can you have one neural network function to even represent this kind of discontinuous solutions? Right. So the idea is very simple. We introduce this discontinuity capturing network So if you have a function in 1D, let's for example take 1D example like this one, where you know that there's a jump discontinuity here, you can just shift it or kind of embed this function to two-dimensional space by you putting this part to be here and the other part to be, say, z equal to 1 here. And this direction is z. So z equal to -1 and z equal to 1. So yeah, so to learn this function using neural network, we are learning, instead of 1D neural network, we learn is a 2D network function where we use supervised learning. We have only the information along this line and information along this line. And what's in between is missing, okay? So we only know the function value here and here. But once we learn a function, we can project back to 1D. Okay, so we project back to 1D to get our original function. So this is the way we represent this two-dimensional, this discontinuous function using neural network. So this is one example for function approximation of what I just mentioned. So the blue line, I think, is the exact solution, and red dot is a network function, and we have accuracy to be 10 to -7. And that's the learned network function you hear. So this part is this guy, and this part is this one. Okay, but what's between is every time it's different. Okay, but it doesn't matter because all we want to know is really the mapping. Okay. So we design this kind of network structure where you have the input neuron to project firstly to the discontinuity capturing layer, where we have this Z is a category of each subdomain. Okay, so this Z gives you the discontinuity. So our network function from this DC layer to the output layer looks like this one. So they have two inputs, one is the X and one is the category. And the whole network answers is this UNX. Okay. So what's good about this network is that you have direct evaluation of the jump value. So we know exactly how to evaluate this jump, and we know how to evaluate its derivatives. Okay. And also we have universal approximation of this kind of network to any piecewise continuous function. Okay. So we use this network to solve the elliptic interface problem. So as I mentioned, the PINN loss is just to minimize or to find a solution which all the equations are satisfied. So by minimize all the mean square of every equation, so it's the plus x minus f, where this the plus x is, I think I divided beta to the right hand side. Yeah. So you can see this is all the equation is a boundary condition here, and this is a jump condition and normal derivative jump. Okay. Yeah, so just give you some test example where in 2D we compare with immerse interface method. The left-hand side is the immerse interface, and where the number of degree, I think, is the number of match point. And on the right-hand side, we have our network function. The N, I think, is the number of neurons. We have just 10 neurons with totally 51 parameters. We have the infinity norm to be relatively the same with immerse interface method. And also 2 norm is roughly the same. Okay, and also compare with other piecewise deep neural network. Okay, we got roughly the same order of accuracy. So the good point of this network function is that it's very easy to do irregular domain. So this is the irregular domain with a piecewise smooth function. So only one pieces. And then there's an arrow to be 10 to -6. And then it's easy to generalize to higher dimension. In 3 dimension with interface gamma, then this is IIM result, immerse interface 10 to -4 in the infinity norm arrow, while in a neural network we have 10 to -5. Okay. And the coding is much, much easier for this network function because you just press one more neuron in the input layer. And for 6-dimensional problem, you just put 6 neurons in the input layer. Then you can do 6-dimensional elliptic interface problem. So it's 64 with radius 0.6, and the interface is again 64. Okay, so that's a loss function where you train a network. That's the evolution of a loss, and that's the accuracy during training. Okay. Yeah, we go to 10 to negative 4 in a 6D problem. So a little bit of summary for this TE-SHENG, and we use one single network to present a piecewise continuous function. We use physics-informed methodology to minimize the strong form of a PDE. And we capture the jump discontinuity accurately. Okay, and it's much easier to implement. Okay, so for the so the next one is how we this one is what? So it's a continuous function, but with the continuous derivative across the interface. So why is that? Because in the Stokes interface problem, we have velocity and pressure. We know that pressure has a jump, so we need to have a TE-SHENG discontinuity capturing. While for the velocity, you have no slip boundary condition, so it's continuous, but the derivative is not continuous. So we need to have an answer for this one. So again, we introduce our, again, similar feature capturing structure. So if you understand what is TE-SHENG, then it's much more it's more easy to understand this one. So you embed this one-dimensional problem to do but think of this two-dimensional problem, we have just a cut, which is, this cut is smooth, but has a jump discontinuity in the derivative at this single point. Okay, so you kind of have a two-dimensional smooth function and make a cut here, then the one-dimensional restriction will look like this one, which is smooth in each piece, but has a discontinuity in the derivative. Okay, a very simple idea. Okay, so let me show you a very simple 1D test, which is a Green's function. It's one-dimensional Green's function. You have a jump in the derivative at 1/3. Okay, and the exact solution is this one. And if you use a ReLU activation function, which is maximum between 0 and x, then in fact you can write down directly this one-dimensional Green's function using two neurons. Okay, so you can use the ReLU activation function to exactly express this 1D Green's function. The problem is if you don't know that, if you don't know anything, if you just train your network with the ReLU activation function, in fact you cannot find a solution. It's a problem. Yeah. So using our this kind of capturing approach, we can find a solution nicely. Okay, and all the other network fails. So for the triangular one, which is if you use the ReLU activation function to your network, you cannot find it. If you use a smooth activation function, you cannot find it. Yeah, only when you incorporate this kind of capturing approach, you can do it. Okay, so now I want to talk about this feature capturing for the Stokes interface problem. So as I mentioned, the pressure has a jump, so we need to have this continuity capturing neural network here, and the velocity, you need to have a capturing neural network here. So the whole neural network looks like this one, where this pi is the pressure, this pi is velocity. The velocity is a vector depending on 1D or 2D or 3D. Here, 1 or 2 or 3 output. Okay, and we train the whole network together. Both networks are linked via the loss function. And that's a 3D accuracy check. So in three-dimensional space, we have analytic solution here. This part is our feature capturing Stokes interface problem, while the right-hand side is the immersive interface method. And you can see that the accuracy is roughly the same. So we attain a similar accuracy, 10 to the negative 4, 10 to the negative 4, in the infinity norm for pressure and for velocity. And I want to mention again, the present method is much, much easier to implement. So this is a physical example where you have interfacial force looks like, I think this is gamma is a constant, this is the curvature of the interface. Right? Yeah, so a little bit summary of the feature capturing PINN. We introduce a structure preserving layer, and this is prescribed. Okay, so we have discontinuity capturing neural network, we have cusp capturing neural network. So we use these two to solve a Stokes interface problem. And we do more, in fact. So we can use neural network to present periodic function. We can present closed curve, closed surface. So we solve surfactant problem on a surface. So, but I don't have time to talk about it. But this is the result I can show you. And then the next one is a hybrid neural network and finite difference. So again, we want to solve this problem. It's an elliptic interface problem. The question is, can we have a hybrid method to combine the advantage of finite difference and the advantage of neural network combined together to solve this problem? So the difficulty in traditional like immerse interface problem is that you need to, along the interface, you need to find a stencil and you need to find the corrections. Okay, the corrections tell you how much you want to correct for this jump discontinuity and the normal derivative jump. Okay, so we want to use neural network to find the corrections and then to combine with traditional finite difference method. Okay, so the idea is very simple. So the solution will be decomposed into two parts. One capture all the discontinuities, which we call a singular part, and one is regular. Okay, the singular part will account for all the jump discontinuities in the function value in the normal derivative and in the Laplace. Okay. And the smooth part will be totally smooth. So the W, the regular part, has zero jump, zero normal jump, zero Laplacian jump. So it can be solved by traditional fast Poisson solver. Yeah. So, so this is a loss function for the singular part. Again, we use PINNs. So that's a constraint we want to satisfy. So put it here, here, and here, and we train this neural network. Okay, once we found a singular part, then we just combine them together. So this is the accuracy check, the two-dimensional accuracy check. For the Stokes interface problem, the interface is here, the analytic solution is this one, and we have a very clean mesh refinement result. So the hybrid method that I just mentioned is the blue circle, where the 2D immerse interface method is the red triangle. Yeah. And also in the first derivative, we have second order convergence. Yeah, so we can do 3D. So it's the same. We have a very nice second order convergence for this hybrid method. So summary of the hybrid method. So the proposed algorithm has a supervised learning test for any fast Poisson solver, and it's much, much easier to implement. And the numerical evidence shows that the overall accuracy is second order. Okay, we can apply this method to any domain that has fast solvers. And the conclusion for everything, so we introduce this feature capturing network. So the composed neural network has two hidden layers. Okay, and we use PINN stores, we use LM optimizer, and the accuracy is very comparable to immerse interface method. And we also introduce this hybrid finite difference and network method to elliptic interface problem and also to Stokes interface problem. And we obtain second order convergence. Yeah. Yeah, so that's my talk. Thank you.
Thank you very much.